economic growth over this decade as it begins to trickle into consumer and business-to-business applications. AppNexus is an example of a company using big data to transform the advertising industry. Prize for Life is meant to transform the medical industry. Basho Technologies and ClickSlide are also excellent examples of companies using big data and machine learning to impact their respective industries. It is clear that big data and machine learning is going to change everything. And with that, I'm very proud to introduce our first speaker of the evening, who is going to be Aaron from ClickSlide. He is the CTO, and we'll start with that.
Hi, my name is Aaron Franco. I'm the CTO of ClickSlide. Our patent-pending technology can generate a graphic user interface for any API without code. We're a VC-backed, London-based company, and we recently moved to New York to build our product team. You can tweet me at ClickSlide CTO, or you can tweet the company at ClickSlide. We're also on Facebook at /ClickSlide, and we have a blog.clickslide.co. We will be publishing a supporting paper for this talk on our blog, so please keep an eye out for that. Teaching the human machine, a human-first approach to machine intelligence. So there are two approaches used in the discovery, development, and design of machine intelligence. The machine-first approach, and the human-first approach. I will give examples of both, and I will demonstrate that the human-first approach is in fact the only practical way to apply intelligent machines to our daily lives. So the machine-first approach takes a very traditional view to the abilities of computer and human interaction. These systems are designed from the ground up with the machine in mind. Engineers develop software based on machine capabilities, and although human interaction is playing an increasingly important role in these systems, it is still merely a component of the system. The ongoing problems humans face with software adoption are proof that this methodology doesn't work. So it all started with this man. This man is Alan Turing. He's the father of computer science as we know it, and he's also a genius that cracked the German Enigma codes during World War II. He also believed that eventually we would see a computer that could think and reason like a human. And he created two concepts. We know them today as the Turing machine and the universal Turing machine. And this diagram is a representation of a Turing machine. Its input is a binary tape, and it executes a sequence of algorithms on that tape, reading and writing. And when the machine finishes its execution, whatever is on the tape at the end is the solution or to the calculation or to the problem. Now the issue with the Turing machine is that for every calculation or for every input-output relation, a new Turing machine must be created. And this is why he created the concept of the universal Turing machine. The universal Turing machine also has a binary input on a tape, but it's also given the description of a machine. And when it gets the description of the machine, it can execute that Turing machine on the tape. Essentially, the universal Turing machine can mimic any other machine. So this is where, he applied these concepts to this computer, which is called the Pilot Ace. And the Pilot Ace was the world's first multitasking general-purpose computer. It's most famous for calculating the cause of a series of plane crashes in the 1950s. So you can see that this machine has no human element whatsoever, right? It requires someone with the intellect of Alan Turing to operate. And this is what our entire industry was built on top of, this machine-first approach. The next person I'm speaking about is Frank Rosenblatt, who created the world's first computer that could solve problems through trial and error. This was known as the Perceptron Algorithm. It was an algorithmically described single-layer neural network that he invented at Cornell University in 1960. And this is very much the basis for neural networks and pattern recognition in machine intelligence today. Again, you can see from the photo that there's no human element whatsoever to his work. It was either mathematically based or algorithmically based. So this moves into something we all know, which is Watson, IBM's genius computer that can beat anyone at Jeopardy. But this computer has a link to the past. In 1957, a man named Ray Solomanoff wrote an essay called An Inductive Inference Machine. And in this essay, he described a machine that could solve problems using inductive inference. I'm not going to get into what inductive inference is, but like I said, we'll be publishing a paper which will have references to this article, and you can cross-reference that article with the technical videos of Watson on IBM's website, and you'll be able to see the connection. So the theory that, or the machine that he described is a method, if the machine is given enough input, right, it can generate a pool of possible answers for any problem. And provided that that pool of answers it generates is large enough, it should never make a mistake in its solution. Right? So this methodology is very much the basis for how Watson solves its Jeopardy problems and its big data problems and whatever else Watson is applied to. But Watson is completely impractical for human beings. Right? It runs on top of IBM's data centers, and I can't put this in my house. Right? It's not gonna do my dishes for me. As genius as it is. So the human-first approach only considers the user's intent during the design process. Right? The underlying principle is that there can be no learning curve. Right? The user should be able to pick up the device or the software and begin using it as if they've been using it their entire lives. That's the human-first approach. And the earliest example I could find was in 1936, AT&T Bell Labs created a machine called Voder. Voder could mimic human voice. So this was the world's first voice synthesizer. Right? And although Voder had no implementations of artificial intelligence or machine learning whatsoever, it was very much a step forward in human-first thinking in the technology industry, and it paved the way for automated answering services. So now I'll play this video. You can see Voder in action.
The machine uses only two sounds produced electrically. One of these represents the breath. The other, the vibration of the vocal cord. There are no phonograph records or anything of that sort. Only electrical circuits, such as are used in telephone practice. Let's see how you put expression into a sentence. Say she saw me with no expression. She Now say an answer to these questions. Who saw you?
She saw me.
Whom did she see?
She saw me.
Did she see you or hear you?
She saw me.
Right, so they describe the machine as having vocal cords and breath, right? And there's a non-technical person communicating directly with the machine. And not only that, but its design is very similar to that of a piano, something that even in 1936 was familiar to human beings. So this is very much a human-first approach to its design. So the next example I have for you was created in the 1960s, and it was called ELIZA. I'm sorry, I forgot to check before the talk. Is this computer connected to the internet?
Yes.
Yeah. So I'll quickly demonstrate to you ELIZA. ELIZA is a chatbot that was created to test concepts in natural language processing. So we can communicate with ELIZA. Unfortunately, I can't see any of it. Right, and it's just a basic program. The program itself is a machine-first approach, but the implementation of it is thinking about the human being and about the interaction between the human and the machine. This application led to a more modern version called Cleverbot on Cleverbot.com. And Cleverbot is a more sophisticated implementation of a similar program. With Cleverbot, you chat through the robot and it learns to mimic you. And then you can put that software on your website or somewhere where you want your visitors to have an experience of chatting with you without actually being there. And it's quite a bit more intelligent than this ELIZA program. So again, this is a machine-first program that's been repurposed in a human-first way with its implementation. The next thing I'm going to speak about is Roila, Robot Interaction Language, which is very modern. This was created in 2010. And the reason I'm putting this in the human-first approach section is because the creator of this was thinking only about how human beings would communicate with robots in the future, right? How would they speak to a robot with their voices instead of with devices? And that's a very human-first approach to the conceptualization of this language. The problem and the issue with this is that it's a language. It's an artificial language. It has two machine-first issues with it. The first one is that it requires the developer to build a vocabulary, build a grammar, implement some open source libraries into a robot, and then program the robot as to what it's meant to do based on the commands, right? That's a huge barrier. The second barrier for the human is that it's a language. And certainly if you only have 4 commands for the robot, okay, I can see how it might be applied, but if you want to implement something in depth, then the human has to learn a new language. And I've learned a language other than English in my life, and I know how difficult that can be. So it breaks the cardinal rule that there can be no learning curve. And that leads up to Irobot. And Irobot, we know Irobot because they've created a vacuum cleaner called Roomba that maps your home and vacuums your floors. And they also have cleaning machines and things like that. What you're seeing on screen is a prototype of theirs called Ava. And if you can see on the iPad, you see a map. And that map was not put in place by a human being, that was generated by the robot. This robot is an automaton that's designed for autonomous mobility and navigation. and Irobot is specializing in robotics for the house and for the military. So, as I've demonstrated, the machine-first approach has enormous limitations because of what it expects from people, what it expects from the user and the human, right? So Watson, you can't use Watson. You have to be a scientist, right? You have to be Alan Turing in order to do it. But then came a company that changed everything, and they flipped this machine-first model on its head with its iOS platform, right? The iOS platform is the most commercially successful human-first approach in technology the world has ever seen, right? And if you look at it from the perspective of computer science, you can, maybe make a generalization that the apps on the device are Turing machines, and the iOS platform itself is the universal Turing machine that powers those apps. But there's a problem. There's a problem with this, and that is exclusivity. It's very exclusive, otherwise known as a walled garden, right? So good luck getting your iPhone to work with your Windows PC or your Android tablet. I've been there myself, and it's a constant headache, right? So there's no connectivity. There's no integration. It's an isolated instance. It's outside of the iOS ecosystem. It's an automaton. Right, so all examples I've shown you are, in one way or another, automatons. The automatons that were built using the machine-first approach are highly intelligent, but they're not practical, if at all practical. The ones that were built using the human-first approach are much more practical, yet not very intelligent. The Roomba vacuum can vacuum the floor, but it can't do anything else, right? These are isolated instances of machine intelligence, completely disconnected from the environment and the world around them. ClickSlide aims to connect all of these lonely, isolated automatons, making even the most impractical practical. Now, I found in the Wall Street Journal just 2 days ago this article that describes a man with a prosthetic limb, with a leg, a fake leg, and the normal procedure for him is he'll walk down the street and something will be wrong. So he'll have to make an appointment with his doctor, go into his doctor, and have a doctor adjust this manually. And now he's become part of a test group that is using an app that can calibrate his limb. He can calibrate his limb on his own, right, with this app. But again, this is an automaton. It's an isolated instance, right? So imagine, if you will, that you could connect this limb to Watson's brain. And this limb would calibrate itself in real time, automatically, as he's walking down the street, taking into account the environment, the pressure that he puts on his leg in a certain way, the air pressure, the weather, right? And imagine if he could do that with the click of a button. One GUI to govern all machines. ClickSlide. My name is Aaron Franco. Thank you.
Thank you very much, Aaron. That was fantastic. So with that, we're going to invite our second speaker up on the stage, Bruce Toman from Cornell University. He is here representing an organization called Prize for Life.
Thank you. Thank you. Do I need this? Can you guys hear me?
No, use it.
Use it. Okay, I will use it. Is that better?
What?
What? You're recording. I'm recording. I might need an IT guy. Do the rescue. Okay. So while I was talking, so I'm Bruce Toman. I work at Cornell University's medical school, which is here in New York City. Our main campus is way up in Ithaca, upstate. I work in the technology transfer office, if you don't know what that is. My office manages inventions made by our faculty, and our mission is to turn those inventions into products for the public good. We also, of course, seek to make money for the university and the inventor in the course of doing that. I manage medical devices, which include software from our radiology department. I'm always on the lookout for software entrepreneurs, so if anybody would be interested in working on a medical imaging startup, please talk to me. A former intern of mine named Zach went to Israel. Thank you very much. I might need your help with that little Thanks. And she now works for an organization called Prize for Life that I will tell you about. She's in Israel. I'm here, so that's why I'm here. Anyway, so there we go. So on we go. So I'm going to talk about big data in medicine and their prediction challenge that's going on. So big data medicine. Y'all are software engineers, so I don't know how much you know about medicine per se. So I'm just going to talk a little bit about medicine. And I'm failing. Upside down. Okay. So really, I'm going to be short here. So medicine. All right. So technology, as you all know, is applied science, right? We all have iPhones that are awesome and little laptops and this great projection technology because we understand physics very well, right? Semiconductors are based on science that we're able to manipulate matter and understand matter down to literally an atomic level, right? Semiconductors are electron volts. That's the magic, right? We understand physics very well. So we can do amazing things in the world of IT. Now, biology is an infant compared to our understanding of physics and material science. Can we do that video thing? So what goes on inside of a cell is crazy. It's crazy. This is an animation from Harvard. This will be very brief. It might be infinitesimally brief. But essentially, biology is still really a descriptive science. You have billions of cells in your body. Each cell has billions of proteins. We don't understand very well yet how each of these proteins interact with each other. It's not science that we can manipulate into technology, right? If you develop a new small molecule drug to find out if it works, you have to literally test it on thousands of people. Literally. This is craziness, right? I mean, you don't have to take an iPhone and test it on 1,000 people to know if it works, right? It's very much an experimental science. Descriptive. Anyway, so this is the inside of a cell. At least a guy at Harvard imagined what it was like, right? We're just trying to describe and understand this. Like, we do not control this. It's super cool. You can find this on YouTube if you look them up. Okay, can we go back to I think? Okay. Anyway, so I just want to make a quick point. Medicine is not technology yet. Medicine is art. It's experimentation. People are bringing big data to bear. I think that's the next slide. In medicine, okay? But can I do this by hand? Sure. Yeah, here it is. Sorry. Next. All right. Okay. That's too far. Back. Okay. So in terms of medicine, there's two kinds of big data. There's basic biology data. I was talking to a guy earlier today who worked on some of the very first machines that could sequence DNA. And he said even at that time, they were struggling to really try to analyze the meager amount of information they were getting. Today, as you all know, we're quickly approaching $1,000 genome sequence, and the amount of data that's coming out of there is staggering. Even so, right, if you can assemble an individual person's genome, you know nothing about them. Because we now know that everyone's DNA is epigenetically modified. We know that if a gene is expressed in the RNA, there's other RNA that's going to come and destroy that RNA. We know that if a protein is made, that protein will be post-translationally modified, blah, blah, blah. It's complicated. It's a mess, right? But nonetheless, we're gathering mountains and mountains of basic biological data that are helping us to describe what's going on. We have gene sequences, we have protein structures, we have small molecule structures, we can document proteins, etc. Exciting, exciting work to be done there. It's going to make a difference eventually, but it's basic science. We also have clinical data from real patients. There's a couple of kinds of this. As you all probably are well aware, there's more and more kind of patient-driven data. Like you can go to 23andMe and have your genome sequenced. There's patients like me where people go in and actually like enter into a database how I'm feeling today. And then if that person has cancer or someone else has cancer, I'm taking this medicine, how is that affecting you, et cetera, et cetera. And they're actually collecting that data and using that to help each other. And SageBound Networks is a pretty interesting open source startup. It's more patients with diseases reporting their actual stuff. But hardcore clinical trial data is really what's been collected systematically, really for a purpose of understanding, does this drug work or not for this patient? Now, most of the carefully collected data has been gathered by companies. That the companies own it, it's their private property, and they really have no interest in letting it out. But this is where the kind of carefully collected, potentially mineable data has always resided, has been with companies. So, I wanted to say that there's been a move driven by, at the bottom there, the CAMD Alzheimer's disease database. The NIH and the FDA, with our taxpayer dollars, have been working very hard to try to improve access and collection of clinical trial data. And you can Google that CAMD Alzheimer's disease database, and it's going to be a publicly accessible database of all kinds of data from patients with Alzheimer's that is potentially going to really change things. But there's still not a lot of publicly available compiled clinical trial data out there until now. So now I'm kind of moving into the meta part of the talk. So there's something called the PROACT project, which was, we all can read the slide up there, but it was a collaboration of a bunch of academic institutes who went out and talked to, I think it's right now, 7 companies, and convinced them to give for free their clinical trial data. And they compiled all this into a database. Now, I got to tell you, I said, pharma invests a lot of money when they do a clinical trial. They pay people, they train them carefully. When a patient comes in, and how are you doing today? The nurse takes the blood, the nurse asks several questions. It's all supposed to be very carefully entered into a database. That the billions of dollars they've spent on this are going to rest on the results. So please do this carefully. A lot rests on this. Clinical trial data is messy. It's like, even with all this investment, it's still, humans are putting it in, and humans are making mistakes. So it's messy nonetheless. It's the best thing we got. So there's right now 8,000 de-identified patient data records in there, and you can do the rest. So what are they doing with it? All right, actually, I'm going to step, I'm sorry, this is kind of a little aside here. So ALS. So Lou Gehrig's disease. Lou Gehrig, as you all know, was a famous Yankee baseball player in the prime of his career, cut down. The complaint is his arm became weak, And it steadily progressed. It went to his other arm, and he was dead within, I think, a year. And it just kind of blew everyone away. Stephen Hawking, everyone knows, the famous astrophysicist, he has had ALS for something like 40 years. He's a freak. Like, if you have ALS, you're usually dead in 2 or 3 years. If you live a long time with ALS, you live 10 years. He's lived 40, and he's still doing great. So, but these are the extremes. But I always thought Stephen Hawking was kind of a normal, long-term ALS survivor. But no, he's the black swan. Way. But that's ALS. It's a devastating, degenerative disease. We don't know what causes it. We can't cure it. There's only one existing drug for it, and it only prolongs life by 2 or 3 months. Like, if you get ALS, you're dead. It's just kind of a question of how long it's going to take. It's what we call an orphan disease. Very few people have it, which means that in the past, pharma didn't want to invest any money in trying to figure it out because there was no money. This has all kind of changed in recent years. Changes in the industry, but it's still true. For those of you who understand statistics very well, it's because it's such an uneven disease, you need to test a lot of people with your drug to have statistical power to know if it works or not. Because it's a rare disease, few people have it, it's hard to recruit patients through clinical trials. Clinical trials take a long, long time. So you build a clinical trial network, you're paying people, you have to keep this whole thing going longer and longer and longer just to see if your drug works. It raises the risk, it raises the expense, it makes the whole thing harder. And the high expense has also driven companies away. So, what is prize for life? There was a guy named Avichai Kramer, who while he was a Harvard business student, was diagnosed with ALS. He's a fighter and an Israeli, and he said, I'm not just going to lay down and die, I'm going to do something to try to help with this disease that I have. They used the prize model to try to drive innovation. Y'all are familiar with the prize model. I didn't know this, in 1927 there was a prize for aviation. It was one of the impulses to drive Lindbergh. Y'all have heard of the X Prize that kind of led to private space exploration. There was a big DARPA project a few years ago with robotic cars. And more recently, as I mentioned, there was a big prize for a $1,000 genome. And I got to tell you, the scientists I work with, they talk about that all the time. It's not just the money, it's also the ego thing. I'm going to be the guy who cracks the $1,000 genome. But prizes work. Prizes accelerate innovation. So Avi decided that Prize for Life would adopt a prize model to try to drive cures for ALS. So, we have the PROACT database. The first thing that they've done with it is set up a prize. So they've taken, it's $25,000 prize. The prize is already open, already started. It runs until October 15th. They're doing it in partnership with Incentive. There's the URL, sorry. So what's it for? Okay, more of why do this? Okay, $25,000 for the winner. The top 3 teams, one person is invited to come to San Francisco to give a talk about the winning algorithm. Oh my goodness. I need to go back. Where should this be? I'm going to bring you back in time. So I was telling you about challenges for drug development. So one of the issues is, like I said, you need to test a lot of patients in order to find out if your disease works or not. If we had a way to say, you, sir, with ALS, your disease is a fast progressor. You're going to be dead in a year. You are going to die in 2 years. And you're going to die in a year and a half. If I give you a drug and you live 2 years, I know that I've increased your chances by 50%. Sorry, that was bad. Right? Like my statistical power goes through the roof. Because I know how you should react, what the normal course of your disease is, right? So I can do a much smaller trial. So how do we do this? How can we know if you are going to progress fast or you're going to progress slow, right? How what we know. This is the point of the database. Okay. So yeah, it's a prediction prize. We have data from all these patients. We have their a measure of how well they're doing called the ALS-FRS score. On day 1, we have every month that score up until the trial ends. We also have a bunch of other data. We have like what's your red blood cell count, what's your white blood cell count, what's your this and that. All of like they take blood, they test all this stuff. All of that stuff's in the database. So the purpose of the prize, mine this data, predict outcome, predict the slope of the ALFRS score. That's the prize. Sorry. Now, so if you win, if you come up with the best algorithm, you win $25,000. You go to this conference, and you can change the world. You can save people's lives. Not you directly, but your algorithm can drive clinical trials that, in turn, can make a big difference. So some details. I know this slide's a little tiny. So they have this big data set, so they broke it up. So there's an initial training set of data from 900 patients. There's about 135,000 data points in there. As I said, the goal is based on information from the first 3 months, predict the slope. As I mentioned there, it's the single measure that you're going to have for every month. So all kinds of data, and as I mentioned, the data is spotty. If you have analyzed data before, you're going to dig into this database and you're going to start screening. Because you're going to say, I need the ALFRS score for the time 0 for this guy, and it's not there. Like for this row of data. It's actually for 8 of them, it's not there. Your algorithm is going to need to be smart enough to take into account human error in terms of entering the data, because that's the real world, right? So this is a big data challenge, data from the real world that can make a difference in the real world. If you're submitting your solution, so right now it's going on, you can go there, sign up, download the data, start working on it. There's a leaderboard. When you have an algorithm that you think is good, you can submit it. They'll run it on a secret data set and put you on a leaderboard. Sorry, it's on the next slide. Nope. There's going to be a date. Oh, there it is. On October 1st, they're going to give you that secret data set, so you have another set of data points to refine your algorithm. October 15th, you submit the code and a description. So Prize for Life is a not-for-profit. They don't want to take your intellectual property. They don't want to take your great idea. What they do want is that you tell everybody how you did it, right? You're free to like start a company and sell your predictive algorithm, whatever you want, but everybody's got to know how you did it. You got to give away the secret sauce. That's the trade. They'll announce the winner in early November, and the judges are a bunch of distinguished folks in ALS. This prize they're doing, again, I got it back, I apologize. So it's the Dream Phil Bowen ALS Prediction Prize. So Dream is a part of IBM. I don't know if you all know them, but it's a big data analyzing group within IBM, and they especially work on biological data. And a rich guy named Phil Bowen gave all the money to winners. So what do you got to say? But they just call it the ALS Prediction Prize. So, and what's in November is Dream's annual conference. We're going to get to talk. That's it. So the message of Prize for Life is, we have the data. The only thing missing is you. So, thank you. Do you have questions for me?
Do you guys have any?
You can't have any questions. That was awesome.
Any questions?
How many other contests have you had besides just this one while you've been doing this?
That's a great question. And Netta had offered to be here on Skype to answer all these, but I will do my best. So I understand they gave out a prior prize for a blood biomarker. No, not a blood biomarker. Any biomarker that could more quickly show if you're responding to the drug. Right now, the tool they have is what I mentioned, is ALS-FRS score, which is a clinical interview. Like, how is your hand strength? Can you swallow? Can you breathe? These kind of surveys are really blunt instruments. So they gave a prize for a very sensitive diagnostic, and the winner was $1 million prize. And the winner was, so what happens in ALS is your nerves can no longer make your muscles work. So the winning solution was a myography machine that essentially measures electrical signal in the muscle. Prior to that, they also gave a prize for an early stage, like the first drug to reach a phase 2 clinical trial. So as I understand it, this is their third prize that they're doing. There it is. Okay, thank you very much for your attention. You were awesome.
You guys, if you have any questions for Aaron from ClickSlide, so I'm going to give him an opportunity right now. If you guys have questions for Aaron, raise your hand. Questions? No? All right, cool. We're going to have Thomas now of Basho Technologies. And this is going to be good.
Thank you. All right, can you all hear me? Excellent, thanks. Thanks to Michael for setting all of this up, as well as AppNexus for the space. Now, before I begin, I just actually want to say that it's like really cool that Bruce is trying to get people to open source predictive algorithms for, doing predictive analytics against, things in the medical space. I mean, I'm a really big open source nut, and I think that's the type of information that needs to be shared in the world. But without further ado, the title of my talk is Persistence of Data. Subtitle of the talk is Existential Engineering. I'm going to keep it kind of short for everybody. It's not going to be drawn out. In this space, this whole big data space, there's sort of really two groups that exist. There's companies or academics or scientists, engineers that are actually like trying to do things with a whole bunch of data, such as Bruce and everybody who's going to contribute to the prize for life. And then there's people in another camp that sort of try to build the tools to get those jobs done. Basho Technologies, we fall into that second camp. We make a database. It's called React. And in this talk, I'm actually going to give you sort of a bird's eye view, high-level understanding of what that is. So, again, who am I? My name is Thomas Santero. I work for Basho Technologies, technical evangelist. Basically, I go around the world and talk to people about open source technology, databases, and React specifically. You can tweet at me if you're interested in that sort of thing, at @tsantero. About Basho, we're about 3-4 years old, pretty well funded, we're distributed all around the world. We've got offices in Cambridge, London, San Francisco, and a lot of our engineers and employees pretty much work wherever they live. We're looking always for smart, intelligent, talented people to hire, so that's my shameless plug for tonight. So, to begin my presentation. In the 20th century, Sartre said, I apologize. In the 20th century, Sartre said that existence precedes essence, pretty much going against the preceding 2,000 years of way of understanding how human beings think about themselves and the world. And this actually really rings true to me. The way that you want to think about data and information is having a decent understanding of who you are, where you are in the world, and when it relates to development of software and dealing with things like big data, you have to recognize that you're going to go through life, and if you're an engineer, if you're a scientist, the work that you do is dictated by the way that you think about yourself, you think about the world, you think about life. What this means is that we're actually human beings, and we're trying to send communications, trying to send information to machines that speak a completely different language. And this is probably one of the main reasons why things don't always work out. Things always break, and just don't operate as we initially anticipated. So instead, you have to try to build your software, you have to try to think about the problem at hand from the point of view of a humanist, in my opinion. And by doing so, it changes the entire way that you're going to approach your problems. So, It's okay, it doesn't fit. Okay, so big data, everybody hears this. I don't know if I'm the only person in the world that's ever experienced this, but I click on a headline, some article or blog that's written by somebody I don't know, just because the term big data was in the title and I thought it would be relevant to me. But you know, after about 3-5 minutes or so, I find myself finishing the article, thinking about, what did I just learn? Nothing. There was like no content in the article whatsoever, and I realized it's probably because this term big data is like a buzzword that means nothing. It has no connotation whatsoever. I mean, React is what some people call NoSQL database. What is NoSQL? I mean, a colleague of mine, Casey Rosenthal, he actually just said the other day, does your toaster run SQL? No, then you got a NoSQL toaster. So I don't really want to get into a platonic talk about, you know, defining everything by what it isn't. I like to try to like bundle things into terms that are comprehensible, because, you know, when I read articles that have blah blah blah, big data in the headline, and I feel bad about it, I mean, like, sometimes I just want to just take my Mac, throw it out the window, and like curl up into the fetal position and start watching South Park to vindicate my existence by means of satire and, you know, things that are topical. But it's really my own fault. What was I expecting? So we should be really clear about the terms that we use to describe what we're talking about. So when I think about big data and try to make some sort of sense of the word, I realize that this is just human beings and machines at ends with each other, because we've got these problems, and they're very specific problems, and big data is itself a problem. And the problems could be anything from working with really cumbersome or unbounded data sets like the human genome, not knowing exactly what kind of data you need, which parts you can keep, which you can throw away, once you actually have it, what sort of aggregation analysis and searching across it that you can do, even if you are able to perform some sort of analysis, how are you going to try to make it comprehensible for human terms? And you know, one of the biggest challenges that we even see over the past couple of years is that gathering this information and capturing it and just putting it somewhere, that's one of the biggest challenges that we have. So when we talk about big data, we're really just talking about the problems that we have. And from my side of things, from my side of the fence, maybe it's different for other people. I think that we're really talking about the difficulty of the tools that we have to solve some really challenging and really exciting problems. So in that sense, I like to think of big data almost as this generation's atomic bomb. Not in a, you know, NSA scary sense that everyone's going to be listening to your phone calls all the time, or that, you know, could eventually, you know, Watson or whatever computer Aaron was talking about is going to become self-aware and turn into Skynet. But rather, this is going to be the source of innovation and entrepreneurial ingenious that's going to carry this generation 30, 40 years into the future and do things like make really smart prosthetic legs. So one of the ways that we can actually solve this problem of big data, it turns out, is by taking a look at a lot of the really interesting and exciting work that's been put into distributed systems for the past couple of decades. It's almost a renaissance, it's the slide, of thought, idea, and thinking about the way that we can actually manage making our computers work for us and using multiple computers at the same time to accomplish some sort of common goal. That is, you know, what a distributed system is, after all. So, with this approach, we have to recognize that what we're really going to be paying attention to moving forward is the way that we deal with our data. This is our access model. The decisions that we make to keep or to leave data out, where we want to physically arrange it in storage devices, and so on and so forth, is going to dictate how we move forward and actually build our applications and build our machines. So here you've got a diagram of a distributed system that is quote-unquote called master-slave. If you have any sort of technology in your big data stack like this, and you're expecting some sort of predictable performance, what you're experiencing is a distributed distributed systems existential crisis. So this is basically harkening back to the monolithic or the architectural monoculture that preceded us for about 3 decades as it is concerned, as data storage solutions are concerned. Basically, you take a look at products out there like Oracle, MySQL, Postgres, they're all the exact same database, just with different switches and knobs and ways that you can, and even the model to interface with it is exactly the same. And what this is just a way of trying to take the problem of big data and squeeze it into that tool that we already have. And quite frankly, you're trying to put a round peg into a square hole and it's not going to work. So there's other tools that exist out there. Riak, which is made by Basho, it's not the only tool out there. There's no such thing as a silver bullet. I'm not saying that this is a database that can solve all your data storage problems, but it does fit very well into a lot of people's use cases. And I'm going to talk to you a little bit about Riak, how it operates, and what it's actually good for a little bit. So basically, first thing that you need to know is that Riak is an open source database. It's Apache 2. We developed it at Basho in the open on GitHub. You can watch it, you can download it, you can resell it if you wanted to. That's how permissive the Apache 2 license is. We do have an enterprise version that we do resell that comes with a support license and 1 or 2 additional features. But for the most part, Riak is going to, the open source product is going to get many people, enterprises, startups, individuals, very far. So what exactly is it? It's no SQL database. It's distributed, so it's a database that you can use to store information on multiple computers, and all these computers are going to behave in such a way that you can think of it as one database service, if you will. It's written in a programming language called Erlang. Does anyone here program Erlang? Show of hands. Oh wow. That's about 3%. I think. That's really good. You go to Erlang conferences, or at least I do, and it's the same 50, 100 faces, like everyone, no matter what city you're in the world. So Riak is a database that's designed to achieve 2, 3 really main things. One, it's a highly available data store, meaning if at least one machine is still alive, you're going to have some sort of access to your data. You're going to still be able to write to it. This is good because the existentialist in me understands that I have to recognize that death is always going to happen. And the IT engineers in here know that death for hard drives or motherboards or network failures, things blow up in the middle of the night for some reason. Never during the day the failures happen. So, if you think these late night heroics make you awesome and a superhero or even vindicate your salary, that's cool. If you run Riak, you can still get the call at 3 in the morning. Your Nagios script alerts you to some sort of failure event, but you check to see that your application is still running, still serving assets, all the data is there. You can go back to sleep and fix it every morning. True story. So it's highly available. You're never going to see anything like this. It's a 404 message because Riak is actually built for the web, if need be, has a native HTTP interface. So it's actually very suitable for somebody that has a startup that is offering some sort of service, or whatever the case may be, where they want to serve assets via the web or via mobile. But it's also useful for enterprise and many other things. So looking at it a little bit closer, this is not some sort of satanic diagram that you have to sacrifice a chicken to install Riak and start storing data. This is basically showing you that the default configuration of Riak is in a cluster. All the nodes are going to speak to each other if they can, but they all operate independently of one another. What's going on node A has nothing to do with what's going on node C, and vice versa. And that's the nature of most distributed systems. We'll talk a little bit more about some of the trade-offs that you may need in a little while about that. So, it's a database, you store stuff into it. How do I store it? It's a key value database. So, Riak doesn't care what you put into it. You can be storing a JPEG file. You can store blobs of binary data. You can be storing JSON documents, XML, plain text. whatever the case may be, it's simply you assign something a key, that something is a value, that's your payload, and those two things with a little bit of object metadata, such like a content type for understanding exactly, you tell the database what it is, that would make what we call a React object. And that's the fundamental unit of replication in the database. We'll talk about replication in just a bit. So once you got all these keys and values attached to those keys, we logically group them into something that we like to call buckets. It's pretty intelligent, right? Buckets. So you got your blobs and buckets. Buckets aren't like tables or anything like that for anyone that's very familiar with relational databases. It's really just a sort of a logical namespace for ordering and organizing all of your data. So if you ever wanted to go and get some information out of a React database, essentially you just call it by supplying the bucket name along with the key name, and your payload, you're going to return a value. So I said that React's highly available. You're never going to not find a princess. And we use a couple of different things in order to achieve that high availability. Replicas. Every time you store an object into React, you have the option of having it copied several times. By default, this is actually 3. So if in the event that one of your nodes in your cluster goes down, there's a good chance that that data exists somewhere else in the database, and you can still write to it, update it, you can still request it if you want. That's one of the ways that you have a lot of durability. On the flip side, though, having a highly available system brings into context something called eventual consistency. We'll talk about that in a little while. But we have ways to tune the consistency model by means of something that we call request forms. A form in React is the number of nodes that have to participate in an event, such as a request, for it to be successful. So for instance, I've got 3 copies of my data in my React database. My read form, if it's set to a value of 2, means I'm going to wait. I'm going to send a request to React. It's going to contact all 3 replicas that live wherever they live in the database, and my request is going to be acknowledged and successful when at least 2 of those come back to me. I can set the read form to 3, I can set it to 1, whatever the case may be. Obviously, the more replicas you're waiting for a response from, is going to be the longer it takes for your operation to actually succeed. So when a node goes down, we use fallbacks. If one's server is simply not responding in the event of something blowing up, as it does, what's going to happen is the database is going to recognize this and then just assign someone to take care of all that work in their stead. So we've got blobs and buckets. We access our data by looking for a bucket and a key pair. And the way we do this is every time that we store the data into React, we use a consistent hashing algorithm. So how this works is pretty simple, actually. We've got this huge key space. It's 160-bit integer, 0 to 2 to 160. For anyone that's curious exactly how large that is, that's more iron atoms that exist on planet Earth. So I think we could fit some big data into React. What we do is we end up taking this key space and we divide it into a fixed number of evenly sized partitions. In this diagram, would be 32. So the nodes that make up your React cluster are then just going to start claiming responsibility for each of those partitions in a roundabout fashion. This way, when we go to store our data, we apply a consistent hash to the bucket and key. In this case, it's meetups, bucket, and NYSE for the key. And it's going to map, the consistent hash will map to a physical number in between 0 and 2 to 160, find exactly which partition that data is supposed to go to, and then it's going to store it to that partition, and then the n-1 partitions that follow everywhere. Now, if you have big data, you want to make sure that your database system can actually scale to make sure that you store. You want your database to grow with your data. So scalability, we've got actually two types. We've got horizontal scalability, which is basically getting what you pay for. I say I add twice as much X to get twice as much Y. In this case, if I have twice as many servers, I want twice as much storage capacity. Pretty simple. And then you've got this concept of vertical scalability, which is the cost-benefit relationship that you have by adding twice as much. It's what you actually get. I add, in the case of Riak, twice as many computers, twice as many servers. I want to get twice as much throughput for my reads and my writes. I want to get twice as much storage capacity, and so on and so forth. Okay, so again, for existentialists, we want to think about death and the way things could end. Say a node blows up. Happens. As I mentioned earlier, it's a highly available system. So anytime that we're going to be making a read or a write request, we're going to elect fallback. In this case, it's the little blue guy. Node comes back online because you've got an awesome DevOps team that spent 20 minutes figuring out what the problem was, I'm sure. What's going to happen is the fallback is going to give all the data that the original node missed while it was out, and then your normal operations are going to resume. So the title of my talk actually pays homage to Salvador Dali's The Persistence of Memory. It's probably the most recognizable painting in surrealist art. I really like it because there's so many ways that you can just interpret this image. Some people like to say that, Dali himself said that the melting clocks image was really his representation or inspired by some melting chemical energies out in the sun. I think he was just not really interested in talking to that reporter at the time. But I agree with a lot of other people's interpretation that this is sort of the unconscious our unconscious recognizing the relativity of space and time. Einstein was really big when Dali was painting this. It makes me think about distributed system and this topic that I mentioned to you earlier called eventual consistency. So eventual consistency textbook definition is basically the time window after or during a failure event, like when our node goes down, that there could be some data in a distributed system that just doesn't agree. It's commonly misunderstood as an eventually consistent system will cause data inconsistency. That's not exactly how it works. But in the case of, I'm storing 3 copies of something in a React database, one of these copies lives on a machine that blows up. I try to update this during a failure situation. There's a good chance that that machine, when it comes back, doesn't know about the new update, and then it's going to actually be serving old data. Well, like I said, with the quorums with React, you can actually tune the level of consistency, make it weak, make it strong. But math dictates that if you're so long as your read and your write quorums added together are greater than the value of the number of replicas that you actually have, you're always going to be consistent at getting consistent data. A lot more smarter people than me have actually proved that, and there's plenty of resources online that I can actually point you to if you're interested in how that all works. So that being said, React isn't just a direct key lookup. That you have more ways to get your data out. One way that you can query against the React database is by running MapReduce queries. MapReduce is a concept that's popular because of Hadoop these days, but really a lot of innovation and work went into it over at Google in the beginning of the 21st century. The whole idea is querying in parallel. It's really expensive to move a lot of data around. So instead of grabbing all of the data that you want to analyze out of a database first, you actually just send your computational logic to where the data lives. So in the case of React, you send a MapReduce query out. You basically say, I want to run some sort of analysis on this list of keys. So send my functions down to where to each node where the data lives, map it all out. The reduce phase is going to produce do some sort of logic like sorting or aggregation or counting or whatever the case may be, and eventually the database will send you back the result that you were looking for. So that's one way to do very powerful queries against the data in your database. You can actually, we also have a feature called React Search that provides you the ability to search for the information in your database, not by assigning it a bucket and a key to look for, but actually by searching against the value itself, and it's going to tell you which object that is. That's what full-text search does. And we also have a way to get to your objects by means of secondary indexing as well. So that's a really high-level view of React. I encourage you now to just go forth and scale by downloading React off of GitHub or off of Basho.com. Play with it, break it, let me know what you think, if you think it might be suitable to your needs. So I'd like to thank you and ask right now if there's any questions. Yep.
When you try and pull data out of the database, like, can you say, I don't want duplicates, so that you don't get a bunch of duplicates?
I'm sorry, can you repeat the question?
What happens, like, because it creates duplicates, right? So, like, what happens when you're trying to get that data? You're going to get a return of a bunch of duplicates, right?
No. I understand. So the question is, since we're storing replicas of data in the database, when I go to fetch an object from the database, am I going to be getting a whole bunch of copies back at once? The answer is no. The copies are there just for resilience and durability in the event of things like failures and such. What's going to happen is when you actually do your query, the server itself, React, is going to get back a number of different replicas, and it's going to compare them to make sure all the values match. And then it's just going to return the result to the client, to your application logic. To you. Make sense? Yes?
I didn't see like a hub that does that logic. They don't look like people didn't know. Where does that decision made? The comparison with replicas.
Okay, so the question is, how does React, or where does the decision get made to understand which replica, to make sure that the replicas are the same? So that's actually handled by React itself. Every machine that exists in a React cluster is going to be running an Erlang virtual machine. And there's a subprocess on there that at request time is going to, the way a request actually works, let me back up, is you can hit any node in a React database to service a request, even if that node isn't responsible for storing the data that you're looking for. So what it's going to do is going to asynchronously send out as many messages as necessary to the nodes where the data lives by applying a consistent hashing algorithm to discover where that data lives. Once those nodes return the data to the coordinating node, the node that you hit your request with, it's going to compare a data type that's built into the metadata of React called a vector clock, which will just define the temporality of changes of your React object. And if the vector clocks match, if the vector clocks match, it's a successful request. If they don't match, they're going to see which one's more current and return that. Essentially.
I just think that the diagram we showed, there's like another node that's on the diagram that doesn't.
Yes, exactly.
Okay.
Yeah, so I guess I'll have to fix the diagram for future presentations. No, that's good. It's clear. Any other questions?
Yes. To compare with speed, how does the speed comparison with normal SQL database?
Okay, so that's a very interesting question. There's a couple of things that I have to say to that. First off, a normal SQL database, for the most part, isn't designed to operate in a distributed fashion. You can shard MySQL and have distributable, but as my slide suggested, you're going to have a lot of problems as a distributed computing existential crisis. I won't go into all the problems with that right now, but if you were to compare a single instance of a SQL server to multiple nodes in a React cluster, it's really just like, you can't make any sort of comparison. Benchmarks for databases are thrown around a lot on the internet, and unless you can actually everything that you've done, including the age of the hardware itself that you're running these benchmarks on, they're worthless to me and they're worthless to anybody in production because there's so many variables that it's so hard to actually just test that. That being said, there's going to be very high throughput in some configurations of React that'll blow a sharded MySQL cluster out of the water, assuming everything is exact in a hypothetical sense that it's actually running on the same exact hardware, the same exact operating system. But on the other side, you need to configure the operating system to optimize for the software that you're running on. So it's a very difficult question. If you're asking the difference between a distributed server and a single server, it's a good intellectual curiosity, but from a production point of view, it's really just not a valid question. You have to understand what problem you're trying to solve, because they solve two different things. Yes?
When do you call it big data versus just the other?
What's the question?
When is it big data?
Oh, when is it big data? I'd say database like React doesn't care about big data in the sense that I want to store everything that I possibly can. I don't know what I'm eventually going to do with it, but just because I can, I want to. I think people use React because they've got mission critical data that they can't afford to lose. If downtime, if not finding the princess actually costs you thousands of dollars a second, that's when you want to put something like React in production. So we care about critical data. When you call it big data, I'm not sure. Maybe exabytes, when exabytes are on my iPhone, as far as storage capacity, that's a lot of text messages.
One of the advantages of relational databases is SQL. And what SQL does for you is basically provides you with the data agnosticity, right? In other words, I can talk to Oracle, I can talk to Sybase. With the NoSQL movement, right? Do you have such an equivalent API? I mean, if I wanted to access, React, I wanted to access CouchDB, do I essentially have to write proprietary code for each of those?
Okay, so the question is, with SQL databases, you have this one standard query language, SQL, that works both on Postgres, MySQL, Oracle, so on and so forth. And in this NoSQL movement, is there a single API that I could use to interface between systems such as React and CouchDB, or do I have to write separate code? The answer to that is you have to write proprietary code. This is one of the trade-offs that you actually make by choosing one of these many new NoSQL solutions that do exist out there in the movement. And it's that you're trying to solve a problem that hasn't been solved before using a relatively new and immature tool. As these tools mature, I can't say one way or another if there's ever going to be some sort of like standardized query language that is developed for all of these. Most likely not, only because the architecture of these databases varies very differently from case to case, and accessing the data inside of them is physically you're physically making separate different types of calls to each individual system. So if you want to have React power an application that you write, you're going to have to write, using React's proprietary client API, which is different from every other database out there.
But, assuming that, I don't know much about NoSQL, that certain principles like follow, right, across all of these databases. So, what makes it so, proprietary or so specific that we can't come up with a common language essentially to express and query it? That's sort of this.
And so the follow-up question is, what makes it so specific that there can be just one universal proprietary or one universal way to interface with all these new databases out there? Well, first off, I will say that React itself does speak in HTTP, so you can actually store and get objects into and out of React with HTTP calls. You can use curl to interface with it if you wanted to, and any programming language out there that can decipher HTTP could essentially be turned into a client library. That said, Basho officially supports libraries for Java, Ruby, Python, PHP, Erlang, and we're constantly adding more. So this, again, like I said, is a trade-off that you have to consciously make, and as existentialists as we are, we understand that we have a responsibility to own up for our decisions, since we have to actually go out there and create our own destiny. That said, moving forward, as these database technologies eventually mature, who knows what can happen. But for right now, every database, because they're designed in isolation from one another, essentially, there's no uniformity. But that's a benefit if you choose to use it. But if you're sacrificing 35 years of predictable hiring and talent pool and experience for technology that has actually been proven to be more effective for a lot of certain cases at places like Facebook and Amazon and Google, that's a choice that you can only make, and it's not magic. There's going to be some things that suck about it too. Yes.
There seems to be a lot of noise to database built once and off. How do you guys differentiate from the other noise skills that are out there?
That's a great question. So how is Riak differentiated from other NoSQL databases out there? First off, I'll say that if you go to wiki.basho.com, we have a pretty objective comparison of Riak at a high level to most of the other major databases out there, like Cassandra, Mongo, and whatever the case may be. So there's literally like a new SQL database written like every week, it seems. And I can't just like go off and listen there. But what I will say is one thing that you get out of Riak that I haven't seen in any other database out there prior to my employment to Basho even, is that there's no other database that's going to be as easy to operate and provide predictable performance that I've personally seen in a distributed nature. That is, if you're trying to solve some sort of problem that requires a distributed solution. Yes?
Yeah, so sort of probably on similar lines, if you were looking at like the, I'm blanking on the right word, like the schema scale or a relation database being able to run into like it's fully relational, foreign key, whatever scale, over here might be doing net cache, it's like pure key value, and one in the middle. Like where exactly would you, well, not exactly, where approximately would you put Riak?
Okay, so the question asked was, how does Riak deal with schemas? The answer is it's a key value data model, and the value can be anything. So if you wanted to create a strict schema that you never deviated from in your application logic by certain things like JSON documents or XML documents, whatever the case may be, that's cool. If you wanted to eventually add new fields to your JSON documents, that's also cool. React doesn't care. Value is completely opaque. And in that sense, there's no strict schema enforcement. Now, if you wanted to use something like Riak Search to perform full text queries against the values of the documents that you're actually storing, what it's going to do is actually, when you store those documents, it's going to create an inverted index and use term partitioning to that you'll be actually getting those indices that you've created to do your search. So if you change your schema, after you've stored a whole bunch of other stuff, it's just going to start indexing more fields as well. So it's very, very loose.
So is there any functionality, so, like with Mongo, you do have the ability to do atomic operation on a field with any document, so is there nothing like that with Riak? You have to pull the whole thing out before looking back in?
Yeah, so the question is there any sort of MSD? Can you do atomic operations on objects in Riak? No, you got to pull the whole value out.
Is there a, sorry. Like when you pull it out, can you lock that row over it, or that key, I should say, or anything like that, or not really?
No, we don't put locks on our data in a distributed system, because then that's just going to cause everyone else to wait. And that's like the antithesis of why you want to build a distributed system in the first place. There's not supposed to be a shared local state, so you can actually perform in the event of failure situations. Because if you actually lock things down, one node go down would potentially say, let the operation proceed or make it fail. And we chose to let it proceed, and that's that. But I will say, because you're interested in that, is the full text search is in the middle of a major upgrade right now, so if that's something that interests you, that's some code I would want to launch off GitHub. Yes?
So I think you mentioned there is this default 3 nodes suggested. So if you increase number of nodes to, let's say, 20, the response time is dramatically slower, because now you have to replicate every tree from one tree.
So the question is, does adding more servers actually impact the response time? It actually does. It makes things quicker. And what I mean by that is because if you add, you have a 5-node cluster and then it goes to a 20-node cluster, you still are only going to be contacting, if you have 3 replicas of your object, you're only ever going to be contacting 3 replicas when you're actually making your request. So having more machines in existence isn't going to slow down your request. What it will do, though, is going to make your internal network a little bit more chatty. There's going to be more network chatter because all the nodes are going to be talking to each other through the browser protocol. And it's actually ended up, one of our production users ended up experiencing TCP and casting, making things possible. One of Basho employees, wrote a really good blog article about that, explaining exactly what happened, why it happened, and ways that you can prevent this in the future. So your requests don't slow down, but your network will, there will be more information flying on your network. Yes?
So it accepts duplicate keys?
I'm sorry, say again?
Does it accept duplicate keys?
No. React, the question is, does React accept duplicate keys? The answer is no. Basically, you're not ever going to be able to store one object or 2 objects with the same key. If you try to write an object with the same key of an object that already exists, what you're actually then performing is an update. Any other questions? All right, fantastic. Well, thanks for all your time. If you have
All right, so that is going to convene the first technical event for New York software engineers. We do have an employer candidate speed dating event planned for next Thursday. It's going to be at NYSE. If any of you guys are looking for a job currently and you have working code, you can show your GitHub, you can show a working application. There's several startups that are going to be there, over 30 employers, and they're looking for talented engineers. So maybe you really want to have working code or something to show these guys, before you go. So that's something to consider. With that, we're going to have more events coming up in October. We have another machine learning event being planned at Newton currently. There's an event going to take place on, I don't know if you guys have heard of Bitcoin and the virtual currency. We're also going to be doing an event on intellectual property law. This will all be happening in October. So that's something you guys will probably want to be coming to. With that, is there anyone in the audience who has a project, a software engineering project that they wanted to speak about for like maybe a minute or 2 to tell the audience if you're working on anything really cool? Anybody?
Can I say I'm a recruiter?
You're a recruiter. No recruiters. No, it's got to be a software engineering related project. Anybody got anything cool they just want to say a word on or anything? Good? Sometimes it works in San Francisco. There's a lot of people who want to come up and talk about their projects. That's why I'm asking. So, cool. Well, with that, I want to thank AppNexus for really, being generous and donating this space. Fantastic. I want to thank Aaron of ClickSlide and Bruce from Cornell and Prize for Life, and also Thomas from Basho Technologies for speaking. Really fantastic. Our first event, I think, went pretty well. So with that, I'll let you guys start networking. We could probably stick around another 20, 30 minutes and network. I think that would be reasonable. And then we should probably clear out. All right? Good. Thanks, you guys, for coming.